Hello and welcome. Now let's take a look at the nacelle and the structure of the nacelle. And start with the so-called rotor hub. The rotor hub absorbs the forces of the rotor blades and then transmits them to the inside of the nacelle. Among other things, the rotor hub also contains the rotor pitch mechanism to adapt the position of the rotor blades to the current wind conditions. The forces of the rotor blades are then transmitted via the rotatory motion to the rotor shaft, which is held by the rotor bearing. At the bottom of the nacelle there is a toothed rim by means of which the orientation of the nacelle can always be turned towards the wind with the help of the yaw drive. Most wind turbines have a gearbox that translates the relatively low speeds and high torques of the rotor side into high speeds and lower torques on the generator side. In the end, the frequency of 50 Hz must be achieved on the grid side. That means 50 cycles per second, which is much faster than the rotor turns. Behind the gearbox on the fast side is the rotor brake. The brake is used to hold the turbine in place during maintenance work, for example. The actual braking process in wind turbines is carried out aerodynamically via the pitch mechanism of the rotor blades. Only the final locking is done via the mechanical brake. Finally, the shaft of the gearbox is connected to the generator via the high-speed shaft, which converts the mechanical energy into electrical energy. Then there are a number of other elements in the nacelle. These include, for example, the electrical and hydraulic controls or the wind measurement system, which is used to adjust the nacelle to the wind direction and the rotor blades to the wind speed. Next comes the cable connection that carries the electrical energy down into the tower. This is where a frequency converter is located in the vast majority of wind turbines today. This enables variable speed operation of the wind turbine so that the rotor blades can be adapted to the wind speed and can always be operated with the optimum aerodynamic efficiency. On the grid side, a fixed frequency, for example the 50 Hz in Europe, is required. The adaptation of the variable frequency of the current coming from the generator forced by the rotor is then converted to the grid frequency with the help of the frequency converter. Finally, the generated electricity is fed into the grid. For this purpose, the voltage is transformed in a transformer to grid voltage that is usually medium voltage or in larger wind farms the high voltage. Thank you very much.